right, it's past 3:30. Good time to start. Reminders. There is a homework due on Wednesday, and whatever it says on the website, due by midnight. That's Eastern time. South Bend is an Eastern time, surprisingly. So keep that in mind. When we say we would like the homeworks to be typed, we mean we would like them to be typed. If you cannot type because you have issues with typing, you can scan it and send it as a scanned document together with your software. But next time, I will also scan my notes and give you handwritten notes as well. So our lab will be mutual, okay? Because when you write these long equations, unless you type them, you will never know if they're right or wrong, right? So there's a reason for that. The next homework has been posted. And it was posted because the deadlines, they are not going to be as nice as homework 1, where he took off for 3 weeks. And, you know, so things we need to basically be sure we cover certain things. So the good news regarding homework 2 are lots of the problems and the software, you can find it here and there. But still, to be able to run it independently, to run the specific cases, it takes an effort, okay? So in some sense it looks long. Actually it's very short, because with some minimal effort you can find everything you need. So the homework, I'm going to use it as a guide for what I do in lectures, because I keep realizing that this is, I think, what the 7th, 8th lecture, and really we haven't done very much, okay? And because simply this area is huge, so my apologies, but I'm going to drive myself from the needs of the homework. In other words, if I see something that's in the homework that is due on Monday, I better cover it, even if it is not important, simply because it's in the homework, okay? And the last reminder is, if you receive that email regarding projects, I would like to have abstracts the way that we describe it on that email by the end of the month, okay? And if you're not sure and you think that I'm going to send it back as not acceptable, send it earlier than later, okay? And all right. So now with that said, we have to cover topics. Half of the lecture today, I changed my mind about 3 minutes before I came down here, because I look at the homework and I say, we're going to be in trouble. So if anybody printed the lecture, I have advised you not to print them anyways, but if you printed the lecture, there have been a few things that have been editing, okay? All right, so we're going to talk a little bit about hierarchical prior models, okay? So the slides contain a lot of information about prior modeling. That's a huge area. I mean, you can do your PhD in that area. But I want to talk a little bit about hierarchical prior modeling. And I believe I gave you 2 homework problems in that area, okay? So some of them are already in the notes, but you will have to work up the details. And then I'm going to start a discussion about model validation and model selection. Basically, that is extremely important areas I want to spend on Wednesday, maybe at least half of the lecture on that topic. So today I'm going to be jumping in a random order, since this is a course in probability, right? So with that, I can be justified. So I'm going to jump to slide 15, which may not mean anything, because by the time I go in the office, the slides may change, okay? So I wanted to give you a nice table that I located in, I believe, in Robert's book, that shows all the exponential family distributions, the most common of them. And on the left column, you see the likelihood models. On the second column, you see the exponential family distributions, that they're conjugate to this likelihood model. So then you can basically convince yourselves that going from the going from the prior through the likelihood to the posterior, effectively what you have to do is update the parameters of the prior, and in all distributions you can see that is the case. So actually, if you want to do exercises, you can try, I mean, most probably this was in the homework, right? But you can immediately convince yourself that the rest of the distributions do make sense. Right. There is a few details regarding the Gaussian with unknown mean and variance in the notes that we already have covered, and potentially part of the proof is in this lecture for what you need in the homework, but maybe it's already contained in another lecture. Okay, so let me jump to a topic about priors that is going to be in the homework, on homework set 2, that has to do with using mixture of conjugate priors. So suppose you have decided that using a conjugate prior is not the right way to go. Okay? Maybe it's uninformative, maybe it's not robust to outliers. You say, this is not what I want to do. So a possibility is to actually use a mixture of conjugate priors. And in the discussion, I'm going to show you that actually if you use a mixture of conjugate priors, it's also a conjugate prior. So you're covered, okay? And here is an example. Let's say if you do this is in the homework set, if you do the coin experiment, so theta is the probability of being heads, and you're not sure if the coin is a fair coin or not. So what you want to do is, you want to use two prior models, one that says yes, the coin is fair, and one that says no, it's not, and put some prior probabilities on the validity of this model or that model. In this case, they're 0.5. Okay? So, so the first thing we need to do is we need to show if the posterior, we need to show that basically that this mixture is also going to be a conjugate prior, and of course we need to show how we're going to compute the posterior, and if the posterior is going to come to be sort of the same form. That would be nice, right? So you can imagine if you have a mixture of this two exponential family distributions, and the posterior comes to be similar with updated parameters and updated coefficients that you mix, right? You don't expect the posterior to be 0.5 and 0.5, all right? So if that happens, then it's great. So let's take the very general case. We take a prior model to be a mixture of these K models with priors pi I of theta. And here for convenience, I'm taking that the parameters theta are the same in every model. So if you want really to push it further, you may argue, well, does this need to be the case? But right now, the parameters basically are common parameters. So, before we had beta models, right? But you can do other things as well. All right. So the posterior will look like, if you follow the algebra, I'm going to go through it fast. It comes out to also be a mixture of conjugate, basically posteriors, all right? They look like the prior, or they're updated priors. So this posterior is basically the posterior corresponding to the prior pi of I. So the calculation is very simple. Let's look on the first term. What do I have? So what is the, it says the posterior, actually our data set. So what do I have on the numerator here? What is f of x given theta? That's our likelihood model times the prior, which is basically this, and I divide this by what? A normalization factor for our combined, basically, mixture of K models, right? So I need to normalize the numerator. So this is the integral that does that, okay? So basically I'm going to have an integral over the parameter space of the likelihood times this mixture, and I basically exchange the integral and the summation. I put the summation outside. So let's call this denominator A. I can write this as Wi divided by A times the prior for each model in my mixture times the likelihood. And then what I have done here, simply I divide it by this integral, which is really the marginal likelihood for model I, and I multiply by this integral. So basically, if I can go to the next equation, Wi prime is basically Wi over this marginalization factor times this integral here, the way that you see. So this is, of course, done so that these coefficients are really mixture coefficients, so they sum to 1. Okay? So the posterior has the same form. That's very nice, all right? But you will, to be able to do the analysis, you will have to compute the posterior for each model I, and also you're going to have to compute Wi prime, which are the posterior mixture coefficients. All right, so usually, I can sit here doing a mistake and say I use the same Wi, but not, because you notice this Wi prime involves the data x. So basically, it needs to contain your updated information once you observe data as to how these two models mix together. So let's do an example, and this is, on purpose, I basically put way too much things on this slide because this is your homework problem. So you basically have to duplicate these results on this slide. So let me go rapidly through it, and I will be happy to answer 2 questions today, but not on the rest of the week, okay? So this is a good time for you guys to pay attention. So it's the coin problem, and I have, let's say, this is my fair coin, this is the not fair coin, and I use mixture of 0.5 coefficients and 0.5, and I give you these parameters for this beta distribution, all right? And we do an experiment, we collect N1 heads and N0 tails. We already have shown that the posterior is basically a mixture of 2 beta distributions, all right? Now, you're going to have to solve this expression, but I want you to look at it carefully and first tell me, you agree with me that these are posterior coefficients, right? This is the data that we collected, so these are not 0.5 and 0.5. They are the updated posterior values of z, where z is sort of a hidden variable that tells me which model I am, which model do I select, the fair coin or the not fair coin, all right? So obviously the data provides some evidence as to what value z is, and that's what I need to use in the posterior distribution. Now, regarding this, the mixture of these 2 posteriors, do you have any problem? Do you think this is common sense, basically, that for the fair coin, this posterior distribution, if I was on the fair coin model, it is basically a beta distribution with these 2 parameters? Are you comfortable with that? Remember how a beta distribution looks, right? Theta to A minus 1, 1 minus theta to B minus 1. And the likelihood here is a binomial likelihood. So theta to, let's say, N1, and 1 minus theta to N0. So are you comfortable that the parameters, if I was in the fair coin model, are these 2? I want to hear a yes. Yes, thank you. And I want to hear a no. Best of luck. My friend Nick will be able to help you on that. So, come on, I'm joking here. So, this, right, so this is the prior that you have to use if you're in a fair coin. So this distribution looks like theta to A1 minus 1, 1 minus theta to B1 minus 1. That's a beta distribution. And the likelihood model has the same conjugate form, which is theta to how many heads you have, 1 minus theta how many tails you have. So when you multiply, you get theta at n1 plus a1 minus 1. So the first coefficient is a1 plus n1. Makes sense? All right? Coins and binomials and beta, right, should be the easy thing. And certainly in this problem, there are more complications we need to worry. Okay? So, since some of you may not understand completely from where this comes, that's what you need to do is you need to prove it in the homework. Okay? So at least you do this calculation. The calculation, by the way, it's one line, but do this calculation. All right. How do we get these two coefficients? So to compute, and this is sort of a standard type of calculation, I'm going to use Bayes' rule. So do we understand how I go from this to this? Interestingly enough, the way this expression is written, right, there is no theta. Somehow I have integrated theta out, so this can be problematic in the way you compute it, but I would like you to tell me if going from this to this is a forward application of Bayes' rule. You're okay with that? Right? So P of z equal to k is basically my coefficients, the prior coefficients 0.5 and 0.5, and this is the marginal likelihood for each model. So to be able to compute these posterior coefficients, you need to compute this. You need to be able to compute this term here. So how do you compute the marginal likelihood for the fair coin and the marginal likelihood for, the other model? How do we compute this for z equal to 1? So if my model, this was my prior and I had a fair coin, how do you compute the marginal likelihood? Because that's what it is. You remember, think of in the posterior of theta, right? Think the Bayes rule. You have the posterior being the likelihood times the prior, and then you integrate the numerator in the parameter space. That's your marginal likelihood. So what is this term here? Is an integral of for the fair coin. You look at the fair coin only. So what is this term? The integral of which distribution? What is your prior in this model? Is beta with parameters say A1, beta 1. And what is your likelihood for this model? Is the binomial distribution, right? Okay? So basically, you can compute this for k equal 1 and k equal to 2, all right? But you have to perform an integration for each term in what space? To compute this, you're going to have to integrate the likelihood times each of the priors in what space? Theta, in the parameter space. So effectively, you know what you will get at the end of the day? You will get a marginalization of what? I actually even give you the answer. You will get marginalization terms that come from the posterior and the prior. So if this calculation is correct, for the fair coin, do you think this looks reasonable? And from where does it come? So you told me that to compute this term, there is an integral of the likelihood times this prior, right, in the parameter space. And I claim that that calculation gives you this. So I want you to tell me from where each of the terms comes. Where is n over n1 comes? This factorial term there. Comes from the multinomial distribution from the likelihood. Where does b of a1, b1 comes? This is the normalization factor for the prior, all right? And this comes in the numerator, and it is basically the normalization factor of the posterior. What I suggest is, right, and I don't want to feed you this in your mouth, if you don't do the algebra, you will never understand it. So what I suggest you do is, you take this, you write this as an integral of this times the likelihood, and plug in the prior, the beta distribution is, you know, theta to A1 minus 1, 1 minus theta, B1 minus 1, divided by this normalization factor. You do the same thing with the binomial. Then you will see there is an integral to compute which comes to be a normalization factor for a beta distribution. That's the answer. Okay? So, in the homework, you have to work for 2 data sets, and you can, what we're asking you is to show how from a mixture of 2 priors, which is this red prior, you go basically to a little bit more complicated than normal calculations posterior that looks like this. Okay? Of course, it depends on the particular data set, so I'm asking you to work the data set. Now, you can do this by hand, right? And certainly you should do it by hand to compare answers with your little computer program. But if you want to do this, you know, with a little computer program, it will basically take you with, let's say, with MATLAB, no more than a few lines, because everything fits to some analytical form. Okay. As I told you today, we're moving around randomly, but not really. All right, and lots of the things in between are things we already have seen, and the reinforced knowledge from the last 2 lectures, so you should read them again. All right, so I want to talk about a little bit about non-informative priors. I mean, I am not a statistician in the traditional sense, right? But people that are in this business for their whole life, basically they will tell you that if you should never feel guilty of using a strong prior. In other words, if you believe on certain priors, you should use them. Okay? Now, if you have lots of data, who cares? All right? Because the priors will have no role at the end of the day. So you can use what is called non-informative priors. But basically the discussion that I have in a few slides is that if you use non-informative priors, you better know that you may get in trouble. Because a lot of times these non-informative priors, they are not distributions. And they're not distributions because you cannot normalize them. They're what's called improper priors. Now, even though they are not distributions because cannot be normalized, somehow the posterior, if you have enough data, comes to be just fine. So they work. All right? So we need to discuss a little bit about these non-informative priors, because I would say in a significant part of the literature, this is what people use. All right, they don't want to basically be accused that they use way too specific priors, so they use this uninformative prior. Now, of course, I don't know if we're going to do this, but I may give you notes in a follow-up lecture. You know, lots of times people use, let's say, if you want to put a prior on the mean, they use a Gaussian and they put the sigma square equal to infinity. They say, I have no idea what the mean is, so just take sigma square equal to infinity. Well, if you do that, sometimes you do get in trouble. All right? You do get in trouble in more than one way. So, you know, this concept of using classical conjugate priors and somehow pushing the variance to infinity can get you in trouble. All right. So we were talking about the coin problem. So in essence, we just discussed this. All right, so let me go through this. We have we do a binomial experiment. We say heads with probability theta, so theta is from 0 to 1. And so somebody will say, I'm going to use a uniform distribution for theta. And it comes out actually, because of the form of the beta distribution, a uniform distribution is a beta 1-1 distribution. You remember beta distribution is theta to a minus 1, 1 minus theta to b minus 1. So a uniform distribution is beta 1-1. And when you take the mean of the posterior, the mean of the beta distribution is a divided by a plus b. So it comes out, if you collect n1 heads and n0 tails, you basically have to add, this is 1, so you basically have to add n1 plus 1, and then on the denominator you will add 1 to n0 and 1, you get plus 1 here and plus 2 there. So this is interesting, right? This is an informative prior, it's uniform. You say, I have no idea what theta is, can be anywhere in the interval 0 to 1, but when you look at the posterior mean, how is it possible the posterior mean to look so different from the MLE estimate? Right? This is something that may bother you. And in some sense you need to think about these things, because wait a second, so what does an informative means? An informative, I would expect to get this, but now my posterior mean, it's actually different. As a matter of fact, the posterior mean will make sense. For example, if you have never observed heads, all right, it will not give you 0, it will give you 1 divided by n plus 1. Okay? So some people claim, right, and there is philosophical and practical discussion in machine learning books, that this is really not an informative prior. All right, so yes, it is uniform, but it's not an informative. And you know what beta distribution is preferred as an uninformative prior? Anybody has seen it or used it? The answer is a beta distribution 1/2, 1/2. Okay? And you can play with it and do the algebra similarly to what I had before for the mean, and you will convince yourself that this may be a much more useful uninformative prior. By the way, this uninformative prior doesn't come from nowhere, and if I hit the right slide shortly, I'm going to show you derivation from where this prior comes from. Okay, another problem with uninformative priors. So let's say before that you selected the coin experiment, theta is the probability that you get heads, and you say you're going to use it as a uniform distribution. How about if you change the parameterization of the problem? How about if instead of theta, your problem requires that you go to theta squared or exponential of theta? Are you going to see a uniform distribution as you change the parameterization of your problem? The answer is no, and the reason is related to the fact that probabilities are transformed in a way that conserves mass, not probability mass. They are not transformed as functions. So, for example, here, if you choose, let's say, a prior on lambda that is uniform, the prior, let's say, I'm sorry, let's do the opposite way. Let's say we choose a prior on eta that is, no, okay. So h of lambda is constant. So let's take that this is, the probability of lambda is 1, all right? So the probability of theta will come to be 1 times d lambda over d eta, which is proportional theta. So it's not anymore uniform. Right? So this can get you in trouble because parameterization of distributions, it is sometimes very essential to allow you to do calculations. So you may think that something is uniform, but because you change the parameterization, it comes out not to be uniform. So, so let me talk, and this is also in the homework set. I'm going to put all these things up because they're very easy to, and you can read a lot of the details. Okay, so let me talk on what is called a translation invariant prior. So let's assume that we have a likelihood with some parameter mu, and this can be the mean of the distribution, for example, in case of a Gaussian. And the likelihood has the following form, is some function of x minus mu. So I'm claiming that this likelihood is translation invariant, and the definition really it is on what you see on the second bullet. It's translation invariant because if I shift x by distance c, the new form of this likelihood function remains the same just by shifting x to x bar and mu to mu bar. So this function is called translation invariant. So as I move, let's say, if you have a Gaussian distribution and you move the mean, the distribution doesn't change. So if you're going to put a prior on the mean, you need to be sure that it's also translation invariant. All right? So again, if the likelihood comes to be translation invariant, which means, again, moving it doesn't change the form of the likelihood function, so then you need to be sure that the prior is also translation invariant. So the question is, which prior doesn't change as you, as you move in space? Remember, priors and distributions transform as distributions, not as functions, so we need to be careful in the calculation. So the derivation is on this slide, and I don't want to go through all the details because they're sort of simple, and they're based in the following argument. I want basically a prior that when I compute this probability mass from A to B, that remains invariant if I integrate from A minus C to B minus C. So basically, if I shift the whole thing by a distance c, basically the probability mass doesn't change. So if you do the calculations, it comes out the only option is for this prior to be translation invariant to be constant. Right? And constantly we can, the constant doesn't matter here. We can assume that P of mu is equal to 1. And obviously a function, a distribution that's equal to 1, it's improper. Right? If you integrate 1 from minus infinity to infinity, you get infinity. So it's not, you cannot normalize. So this is an improper prior. However, if you have, let's say you think of the mu here to be the mean of a distribution, let's say a Gaussian, and you use a prior that is constant equal to 1, you know what? If you collect one data point, then the posterior comes to be proper. So in other ways, even though the prior you cannot normalize it, with one data point you can normalize the posterior. So the fact that this is not a distribution is not an issue if you have one data point, which is not bad. So you violate a few things, but somehow the posterior works out at the end well. So let's look at the scale invariant prior. So we look at another likelihood that now, if you change the scale of x, sigma here is a measure of a scale of x, all right? So if you change it in a way that the likelihood remains scale invariant, and again, this is the definition. If you go from x to x bar, where x bar equals c times x, if the form of the likelihood remains the same, then you need to have a prior that is also scale invariant. Okay? So, and where is that coming from? So, if you use a very simple derivation, you say you want to preserve probability mass when you scale A and B to A divided by C and B divided by C for any C, and you do the integral there, it comes out that the improper scale invariant prior, and this is very important to remember, it's 1 over sigma. And it's very important to remember because in the literature, you will see this prior thrown here and there, and you'll be wondering from where it comes from. Okay? Now, for those who already have done some work in machine learning, don't get in a panic mode, because usually you affiliate sigma, let's say, with standard deviation, and usually the priors are priors on sigma squared, and the improper prior in the literature appears to be 1 over sigma squared. But here, for a scale invariant prior, this is the correct result. It's 1 over sigma, and it's a prior on sigma, not on sigma squared. I'm going to come back to that. All right? So the prior on sigma is 1 over sigma, and equivalently, this implies that the prior on log of sigma is a uniform, it's constant. Okay? So if you have a scale invariant, the need for a scale invariant prior, then the only way for this to happen is for that prior to be 1 over sigma. Okay. So I need to give you one more formal definition of uninformative priors. Let me just jump this an example and discuss about Jeffreys non-informative prior. Again, this sounds of theoretical use only, but if you read papers on Bayesian statistics, the chances that you have to play with Jeffreys priors are about 100%. Okay, in every other page, basically, we start with Jeffreys prior, and you need to be able to know from where it comes from. Okay, there will be no philosophy here. I'm going to give you directly the definition. So what you need to do to formulate the Jeffreys prior, you need to compute basically what is called Fisher information. And this involves computing an expectation with respect to the distribution of your data set of the Hessian of the log likelihood, right, which is what we call Fisher information. So this expectation, if you take square root, this gives you what we call Jeffreys non-informative prior. And it sounds sort of a mathematical construct, but I'm going to show you that has very nice properties that come for free, basically, that other prior models will not satisfy. Right, so we're going to do some examples, right, but I want you to look at the definition. Take the Hessian of the log likelihood, differentiate twice with respect to the parameter theta, and this can be a vector parameter. Take the expectation with respect to the distribution of x, okay, and take the square root of the, if this comes to be, you know, obviously high dimensions would be metrics. Take the determinant to the power 1/2 that gives you the Jeffreys prior on theta, okay. By the way, this definition and that are identical, and homework problems usually ask you to prove this, but I trust that you know, I think the proof may be even in the slide somewhere. You can look at it. So let me give you one thing that you get for free with Jeffreys prior. It satisfies this reparametrization equation, so that conservation of probability mass automatically. In other words, if you have a Jeffreys prior with parameters phi, once you change from phi to theta through some function h, this equation is automatically satisfied, and you can see the proof on the equation on the bottom. So can you look and tell me from where, you know, so when you try to go from one parameterization to another, from phi to theta, so you go from phi to theta, you start with the definition of I on the left, and then from where do I get this square? From where that term came from? So I change from phi to theta, right? That's my objective. I want to go to a new parameterization, so I can compute the prior in theta. Where did this term come here? So I have second derivatives in phi, now I have second derivatives in theta. Where do I get this? What's the buzzword? Chain rule, thank you. And again, this is determinant because, you know, it can be more than one D. So if you pull this thing outside, it doesn't depend on x. Basically, you get I of phi equal I of theta times this square. So the Jeffreys prior is the square root of that. So you have the Jeffreys prior in phi is the Jeffreys priors in theta times d theta over d phi. So the reparametrization is taken care of automatically. Very nice. All the priors, you know what? This is may not be satisfied at all, and you may get in trouble. Jeffreys priors actually does the job. So let me give you a few fundamental examples, basically, because I think in practice this is what you will be using. So let's say we have a likelihood which is Gaussian, and we take that the variance is known, so we make life easy, and the only unknown is the mean, all right? So our parameter theta is the mean, okay? And we want to have a prior, the Jeffreys prior on theta on the mean. So I advise you to look at this calculation, right? There is nothing there. I am taking the likelihood for n data points, and rather than starting from the primitive form, I am writing this using the sample mean of x. You may have seen this derivation in earlier slides, right? So the likelihood if your n data points looks like that. So what you need to do is take the second derivative of this. The second derivative comes to be minus n over sigma squared. There is no x dependence, so this is constant, this is constant. So Jeffreys prior for the mean comes to be the uniform prior, which is in accordance to what we discussed before about this translation invariant prior. So this is sort of a nice result. It's good to know that Jeffreys prior agrees with this. So let's consider now the unknown variance. So the mean is known, right? But the variance is unknown, all right? So if you do the same calculations, the likelihood looks a little bit more complicated than before, right? Because I have to keep the terms that depend on the variance. So you have this sufficient statistics divided by 2 times theta again is sigma squared here. Take the second derivative with respect to sigma squared. Again, I'm going to compute the Jeffreys prior for sigma squared, not for sigma. You remember before we had the prior on sigma was 1 over sigma. This is the prior on sigma squared. So theta is sigma squared. So this is the second derivative. And now you have to take the expectations with respect to the probability of x. And when you compute this, it comes out that the answer is, we have to take square roots of this, right, to compute the prior. So the answer comes to be that the prior of theta, which is sigma squared, is 1 over theta, which is 1 over sigma squared. This is extremely popular on prior for the variance. The chances that you will see this prior being used in machine learning is about 95% of the time. And notice it is not the same as the prior before on sigma that was coming to be 1 over sigma. Very different. So here the prior on sigma squared is 1 over sigma squared. Okay? And basically this prior, you notice, becomes maximum when sigma is small, so it favors small variances. Now, there are some contradictions with this as well, right? Not everything is rosy. And let's I am not going actually to do these contradictions, but 2 slides further down, it discusses the case of Jeffreys priors when both the mean and the variance are unknown. And actually what you get is you get a result that is very different from the case of priors that are the product of 2 uninformative priors on mu and sigma squared. In other words, if mu and sigma squared were independent, Jeffreys prior gives you a very different answer in that case from what you expect. Okay? But here you need to be consistent. All right? So Jeffreys priors on sigma squared, it comes to be 1 over sigma squared. Okay. All right, now we have to discuss an extremely important topic, all right? It may sound a little bit weird, but it's very, very important. So let me see if, okay. So let me, so in, with this prior models, right, somebody will say, but I don't really have any confidence on any prior. I mean, I'm not sure if it is this or that, and I don't have enough data. And obviously, if you use a prior, it may pull your estimates in one direction versus another, so you're not very happy. And there are many other cases that, they have their own character. So in those cases, what you do is, you start with a prior that has its own parameters, and then on each of those parameters, you put another prior. And then on the prior of the prior, you put another parameter. And you keep going with the expectation that down the road, the effect of these hyper priors will be minimized. Right? So you can think, before when we had the fair coin, we had the parameters, we said pi of theta involves the parameters A and B. Well, fine. So A is not known, so let me put another beta distribution on A with some other parameters, and some other distribution of beta with some other parameters. And you keep doing this a few times with the expectation, which comes to be true, that as you keep doing this, the effect of the final parameters that you stop, because you have to stop somewhere, it will not make such a big difference. Okay? But there is, I don't have time to discuss basically examples where you do this in the scenario that I described. I want to describe an even more important reason why to use hyperparameters in prior modeling. Okay? And at 3 o'clock I was looking to give you a problem on this for the next homework set, but most probably this will have to wait until homework set 3, but let me describe it now. Okay? So we're going to, so we have a prior pi of theta, okay, exactly as we did before, but let's assume that this prior has its own parameters phi. So in our coin problem, phi can be our alphas and beta, and then we're going to use a prior pi of phi. All right? So really this is the parameters that come in the likelihood, but we assume hierarchical model for pi of theta, where we specify the probability of theta given phi, and then some prior model on phi. Okay? So obviously our parameters now become theta and phi. So when you talk about Bayesian inference, you really have to compute the posterior of both theta and phi, which is really you take a problem that is bad and you make it really bad, really worse. Okay? So the posterior of theta and phi, you can write it as the likelihood, and the likelihood I can simplify it because x depends only on theta, so there's no phi here, right? And then I can introduce my hierarchical prior and write this joint distribution of theta and phi as p of theta given phi times p of phi. Okay? So what I'm going to do is I'm going to give you different approximations that you may want to do where you will never have to explicitly compute this likelihood, because that would be way too complicated a problem, and really this is, you don't use this hierarchical modeling to have to compute something very complicated. You do it because you want to gain something out of it, right? So we will find some approximations that don't require this complicated posterior calculation that you see there. And we're going to do one specific example where hopefully you will appreciate the value of this. All right. Don't know what the next slide is because I want to jump to, okay, so I'm not going to do this. So here's what we have. I mean, denoting here the dependencies, right? So my data depend only on theta, and I make theta to depend on some hyperparameter theta. Okay? So this is the notation I'm going to use in the derivations. My likelihood depends only on theta. but theta hierarchically will depend on some other set of parameters that I call them eta. So let's apply exactly that particular model to a very specific model that sort of fits in the scenario of many practical problems in machine learning. Hopefully you will appreciate why you need hierarchical priors beyond the fact that you're not confident in using any specific one. So let's see what the problem is. We consider the problem of predicting cancer rates in various cities. Right? So we collect data in Chicago, in Philadelphia, in New York. We look at the population of the different cities, and we see how many cases of cancer we had, let's say, in a given time period. And I'm going to assume that my likelihood model is a binomial model for each city. All right? So the number of people who have cancer in a city with population n I is a binomial with a probability of having cancer being theta I. And obviously you can appreciate the fact that maybe, one city is more polluted than another. There are more reasons to have cancer in one place than another. So this probability theta I should depend in principle on the city that you are referring to. But if you do it like that, obviously the problem is going to be very complicated, and somebody will say, then I work on every city separately. But you don't want to do that, because maybe in some cases either the population of the city is very small, or maybe there is no cancer cases. So do you conclude basically because you have not any data that there will be no cancer cases in those cities? Well, here's the idea. We want somehow to take this rate of having cancer in the different cities and make it common in all the cities, but link that information to a hierarchical model. So let me go directly on the equation on the bottom, and I want you to look at it, right? N I equal 1 to n is the number of cities, xi is the cancer cases in each city, and ni is the population of each city. So look at this equation and tell me, what do you think it does? No need to read anything, right? So I am going to, my likelihood is a binomial model, all right? And for the cancer rate, I'm going to use a beta distribution. That's a reasonable thing because it's the conjugate to the binomial case. But what have I done? How does eta comes in this equation that you see on the bottom? So to basically account for all cities, right, I have the product of, this is my likelihood basically, all right? I allow theta I for every city to be different, but considering the fact that in some cities I may not have enough information to compute theta I, what does this equation does that links the different cities together? There are something here that doesn't have an I parameter, an I subscript on it. So eta is common. So basically, I'm going to use a hierarchical model on all the parameters theta I, and the parameters on this hyperprior will be the same for all models. So effectively, I'm going to have all the cities to share statistical strength. If in one city my population is small or xi is small, that should be no problem, because effectively I'm going to mix all the data together to compute this common hyperparameter theta. Makes sense? I mean, if you don't do this basically, right, then you will say, I go in every city and I compute, let's say, my maximum likelihood estimate or my map estimate for every city. But what happens if in that city you have 0 cancer cases? So do you declare that there is 0 cancer in that city? Right? I mean, if you collect 50 data points, right, you sample 50 people, there's nobody having cancer. So what do you do? Obviously, that would be the wrong answer. But if some city maybe has a population of 2 million people and you have lots of cases, maybe you can share part of that strength from that information with smaller cities or cases that you have xi that is smaller. So this is hierarchical prior modeling basically at work. Okay? So effectively, we have a prior on the thetas that have the same, so every theta 1, theta 2, theta n, they have the same hyperparameter theta. All right, so we have this nice equation. We mentioned we don't want to compute the posterior of theta and eta because it's nasty. Can you tell me what options may be available if somebody doesn't want to compute the whole posterior of theta and eta? I mean, approximations. What approximations can we do on this structure, all right, without having to compute the whole posterior of this parameter eta? Remember what I was telling you, right, that as you do it hierarchically, the effect of the parameters is diminishing. So if there was no eta, right, of course we have to compute the posterior of this. We cannot use the MLE estimate because if you don't have data, the MLE estimate will be wrong. All right? So obviously we need to compute the posterior of theta I if we work on every city separately. But when we mix this here, if the effect of theta is not as important as the effect of theta I, what can I do to eta? How can I approximate it? I mean, what type of, when you compute parameters, can you tell me what type of estimators we have seen up to now for parameters? I mean, mention to me two estimators for parameters. The first one was MLE, maximum likelihood, and the second was MAP. All right? So can we do a point estimate for eta rather than having to compute the posterior of eta? If we're going to compute a point estimate for eta, the question then is, a point estimate means I have to minimize or maximize some loss function, something. Right? In MLE, we maximize the log likelihood. How do you compute a point estimate of eta? How do we compute a point estimate of theta? Well, our priors are what you see here, right? So this is our selection done, okay? So we need to find something to maximize or minimize, the way you pose it equivalently, to give us a point estimate for eta, all right? And as I said, if it was an MLE, right, you write the likelihood in terms of theta, all right? You write the likelihood in terms of theta and say, this is the maximum, all right? But right now, theta and eta are coupled. So theta comes in the likelihood, not eta, and eta comes from this hyperprior. So how do we define, the only information we have in this problem, it's our data. This is on xi and ni. That's the only thing we know. So what can we do to find the point estimate of theta? Integrate theta out, and what do we achieve if we integrate theta out? Integrate out on what? From where? On what term? You say integrate out what? That doesn't mean anything. It's like I'm integrating you out, means, you can leave now. All right? So what does it mean, integrate out on, what do we integrate out? From where? From the joint. So you are saying, how about if I define the marginal likelihood when theta has been integrated out? Something like that? All right? So how about if we find the marginal likelihood there is no more theta when theta has been integrated out? Is that possible? can you find basically a marginal likelihood where eta is left, but theta has been integrated out? So let me see what the next slide will tell us. Well, I don't have the derivation for you actually, okay? Can we actually integrate theta out here from this expression? And you don't have to worry about this product, right? I mean, this looks like your beta distribution. This looks like a beta distribution. Can I integrate theta I out? Will be difficult basically to do it. I mean, I don't think so. You know why? Because this will give you a term, this term will be like theta to some power 1 minus theta to another power, this theta to some power 1 minus theta to another power, and if you integrate theta out, you get a normalization of a beta distribution. Very easy to integrate theta out. And if you leave theta basically as a parameter in that. And then what you do is you compute theta that maximizes the marginal likelihood of your observations xi in cities with population ni. Okay? So I'm going to show you the results because you can get an appreciation of what this thing does for this particular problem. So we have 20 cities, and this is from city 1 to 20, the number of people with cancer. So this is basically our data xi, all right? So you notice in some cities, especially cities with small populations, we don't really have any cancer cases. I mean, we took samples basically, and our sample did not indicate anything. So this is the population, all right? This is the maximum likelihood estimate of theta I, which we said, if you don't have any data, would be obviously the completely wrong answer. And you can see here, in several cities, it says the estimate for the number of cancer cases is 0. Obviously, you don't expect this to be true, right? Because the population, is significant. So this obviously is the wrong estimate. Now, the plot on the bottom shows two different things. Okay? And I want you to extrapolate what these two quantities are. You remember this, if I go back on the previous slide, my parameter eta is a bit, comes in the beta distribution, and eta is the coefficients A and B in this beta distribution. So remember, A and B is the coefficients, on the hyperprior. So what is E of theta I given my data D? How do I call this with words? What estimate is that? What estimate is this? This is my posterior mean, basically, right? Without any eta or anything like that. So if I don't have any hyperprior, this is the posterior mean of cancer cases for each of the city size. And you notice the posterior mean basically looks like this. The only difference, of course, here, you can define this in two different ways, right? You can define this with 0 hyperpriors eta, but also what you can do is you can define it in a way that eta has been marginalized. And what you see in this calculation, the more sophisticated calculation comes to play a role, where eta was marginalized out. So this is the posterior marginal mean, if you like, of theta I, and these are this blue histogram that you see on this picture. What is now A divided by A plus B? You remember what's the mean of a beta distribution with parameters A and B? What's the mean of a beta distribution with parameters A and B? A divided by A plus B. So what is this estimate here? So it's the posterior estimate of this is the posterior estimate of theta, okay, through the hyperprior model that you see in here. So in one estimate, what we do is we integrate it out. These are the posterior marginals, all right? And this red curve that you see here is computing the theta i's, an estimate of theta I, by involving it directly and using the same estimate, notice, the same estimate for all theta i's. So basically it says, I'm going to give you an estimate for the cancer rates where I use all the data, I compute one set of hyperparameters A and A plus B, and from there I compute one estimate of theta I. So I am pulling all the resources that I have together to give you a pooled average of estimate of the cancer rates for all the cities. And this is what this red line that is given here is all about. Okay? So the idea is, in some cities, we had no cancer cases, right? So effectively what I'm going to do is I'm going to borrow information from everywhere else to compute this hyperparameters A and B, and through this estimate, I'm going to come up with an estimation of theta I that is going to be shared between all the cities. Okay? And since this is obviously, you have distributions, you can compute the credible intervals, basically, your uncertainty in the various estimates. And notice, I mean, you can study actually this slide for hours, right? But let's pick up a few interesting things. The uncertainty, let's say, in city 10 is huge. So let's look back. Uncertainty in city 10 is huge. Can you guess why?
Because that's a large number of people with cancer despite small population.
So the MLE estimate, it seems to be very confident, right? It says I have a lot of cancer cases, I have a big, relatively big population, so this is my MLE estimate. But when you do this pooling of all the resources together, what do? You take that information and you share it, you give it to the other cities to make estimates, which means you pull away from actually this MLE estimate. And as a result, the uncertainty in city 10 increases. So basically, you accept the fact that in places where you should be very confident, now you're less confident because you went away from that information. I mean, you don't want to say, for this city, use the MLE, for the other one, use that, and for this, do this, and do that, right? You want one common estimator for all your data sets, for all the cities, with all the resources pulled together. So you can, for example, I still now, city 15, let's see, what is city 15? So in city 15, you have so many cancer cases, basically, that whatever you do, right, you're on the mark in your estimate, okay, because Xi is very high. And that's why this marginalized estimate of the of theta I comes to be about the same as when you pull resources from the different cities. I believe I have another example like this, but I want you to really study this. I'm going to give you sort of a homework, maybe on set 3, so you can appreciate this. But let me just generalize this problem regarding on the estimation of theta. So we said we're going to use a point estimate for theta. So we don't need to compute the posterior. And the point estimate of theta is the one that maximizes the marginal likelihood that is given inside this integral. So look at this integral carefully, right, and convince yourself that that's a marginal likelihood. By the way, anybody who works on model selection, model validation, this is the calculation you have to do. This is standard, okay? So we want to fix theta in some point estimate, and we fix that in the estimate that maximizes the marginal likelihood. To calculate the marginal likelihood, we have to average over all possible values of theta. And effectively, what I have here is, right, what you get when you write your posterior, the marginalization factor, this is the likelihood, times the prior, integrated. So this is the evidence of your data for each parameter eta. And we select that eta that maximizes this marginal likelihood. Okay? This model comes with different names, and actually I find this name is very sort of misleading. Empirical Bayes basically refers to this point estimate in most of the literature. In books like in Bishop's book, this comes up with the name evidence approximation or type 2 maximum likelihood. Okay, so this, you know, they all mean sort of exactly the same type of things. So again, you compute the posterior of theta, but rather than doing this heavy calculation where you compute the joint posterior of theta and theta, what you do is you fix theta to a point estimate that maximizes the marginal likelihood, and that's the empirical Bayes approximation. So this slide that I copied this table from Murphy's book, it gives you sort of four possible point estimates that someone can do, starting with a maximum likelihood. All right? You can do a map estimation where you keep it at some arbitrary value. You can do this empirical Bayes that we discussed, where you maximize the marginal likelihood. You notice in this calculation there is no prior of theta, all right? But what you can do is you can maximize with respect to eta this marginal likelihood times the prior of theta, all right? So this is more Bayesian if you like. And of course, you can compute the whole posterior, which will be extremely computationally expensive and possibly something you cannot do without numerical exploration. So the most common approximation, again, is between this empirical Bayes that you see here, and if you want to do incorporate the prior on eta, you can do what is given on the fourth line. So you know what? Let me see. Well, I actually give you a reference. All right. For you remember we said we need to compute the eta parameters that maximize the marginal likelihood. And you may say, do I need to compute that whole integral? And I told you don't have to worry because the integral has a closed form, and there is the closed form. You agree? Right, if you write this as theta I to the power alpha minus 1, 1 minus theta b minus 1, divided by this, and this has this normalization factor outside, and then it has theta to the power ni 1 minus theta to, ni minus, sorry, to the power xi, 1 minus theta ni minus xi, times the term from there, and you get a normalization factor for beta. So actually, this marginal likelihood has a closed form solution. So what you need to do is you can do the maximization with respect to the parameters A and B using this expression, which by itself, by the way, can be a little bit nasty. And there is several suggestions in a little report of Tom Minka on how you do this. And even though the paper says for the Dirichlet distribution, it starts basically in the first few slides, pages, with a beta distribution. So you will see the minimization with respect to A and B. You can read this report. And by the way, all of these are linked, okay? And to link them, it takes effort to find these papers. And I do hope by accident, once your little hand takes you and you press it, so a paper comes out, okay? If not now, maybe when you do your project. If not when you do your project, maybe when you do your research. I really want you to take advantage of this type of information because these are very useful sort of calculations. It is 4:45, and I was planning to talk about what was the last subject? Model selection and Bayes factors that also come on homework too. Obviously that will have to wait until Wednesday. So I'm going to remove that portion of the from the slides, and I'm going to put this on the lecture on Wednesday. I have office hours. After I can take 10 minutes of relaxation, but I'm going to be in the office from 5 to 6. If you have any questions about the forthcoming homework, 2, because I hope homework 1 by now is over. Okay? So if you have any questions about that or the lectures, please come to see me. Or about your projects. Okay? Or about your projects. So I will see you at office hours. Anybody wants copies of my slides, because usually I throw them. You want copies?